Hello everyone, this is Karim Sabih with the Process Engineering Tips channel. Today we're going to talk about steam jets. Sizing a steam jets. A steam jet basically a simple device that pull a vacuum from on process vessels or reactors. They're low maintenance and cheap and a good way. Actually, it's a good device. You see them everywhere in chemical plants. All right, so we have a case study. Let's say you want to design a steam jet to pull a vacuum on a reactor, okay, batch reactor. And let's say you have an excess raw material that you want to strip. And say, depend on the cycle time that you want. Let's say you have 1,000 or you have 500 kilogram of that excess raw material, and you want to maybe do that cut in 30 minutes cycle time. Then you could say, okay, my flow of gas is 1,000. Basically, when you're going to design a system, you'll know this information, these input parameters. You'll need them. Now, for the off-gas temperature, okay, say this one is at 40, but this one, like in theory, you will know basically when you're trying to design, right? If you're doing a steam jet for an existing equipment, then you look for temperature gauges, let's say, or if that's not available, then you could just assume the reaction temperature, unless if there are condensers on the top. And if it is, let's say if you have a condenser with the cooling water, you could assume, okay, the same temperature as the cooling water return plus 10 degrees Celsius, and so then you could get that. And depend on the material, you get like molecular weight. Let's say for this one, I'll use 50, okay? Now, let's say, so now you need to define what is your suction pressure of the steam jet and your discharge pressure, okay? Now, let's say I want to pull the cut at 0.8 bar. And now the discharge, it's really depend on what's downstream the steam jet. I mean, if it is something you vent to the atmosphere, then, you could just say atmospheric. So you could just say 1.15, a little bit extra, so just in case. But if that tied into some thermal oxidizer or like a flare, and there are like a line, so there are pressure drop, so you need to leave some cushion for pressure drop, right? Say this one, I want to design it for 1.2 bar, okay? Now, what steam do you have for your steam jet? Say I have a 21 bar, which is a high pressure, which is good. As high the pressure, as actually less steam consumption you're going to need, and more deeper vacuum you could have, okay? So let's say my steam supply in the plant is 21 bar. Then you also need the steam temperature, and that's something, say if it is saturated, then you could just Google, okay, what would be the steam temperature at for 21 bar, and that's like around 215. But if it is like a superheated steam, then you could just use that temperature. Okay. Then now we have all the input parameters. Now we design the steam jets, okay? So I have some equations here and some graphs from vendors. Now the way this, the sizing is that, depend on the vendor. The vendors, they have these charts. Either they're going to have it based on a water equivalent or an air equivalent, but both, they're going to give you the same thing, which is, a factor to calculate the steam consumption, okay? This in particular, this one, which I find online from a vendor website, talks about the water equivalent type of consumption, and so we'll do it based on that, okay? But there are other like parameters. So one parameter that you need to calculate is the compression ratio. So, and the compression ratio is your steam jet discharge pressure over your suction pressure. So that would be this 1.2 divided by 0.8. Now this one is really important. Why? Because this would tells you how many stages of steam jet you need in series, right? Because if it's something above 5, if your compression ratio above 5, then it's not recommended that you have one stage steam jet. You probably would need at least 2 stages, right? maybe you could put it as a rule of thumb, like your compression ratio should be somewhere between 3 or 4 or less. If it is more, then you need to do multiple stages in parallel. I mean, if you are even pulling it much deeper vacuum, then you might need even 3 stages or 4 stages. Okay. And the expansion ratio, that's the steam pressure divided by the suction pressure, and as big as that ratio is, this ratio is you're going to use to for the graphs or the charts provided to find the info that you need. Okay. Now, so we have these two parameters. We need to calculate this equivalent water suction flow. Okay, and the equivalent water suction flow is basically your off-gas flow, okay, multiplied with 2 factors. And these 2 factors you could get from this graph here. There's one called the suction factor and the other one called the equivalent suction flow factor, okay? Now, the suction factor, that would be basically use the steam temperature. In our case, it's like 215, right, our steam temperature. So that would be somewhere here, okay? And then you need the line that you have is for your motive fluid molecular weight. So in ours is a steam, right? But you could use any. You could use like air jets or nitrogen jets. So you could. This method would be not only for steam jet, could be for other jets as well. Okay. So your motive fluid here is water or steam. So it's water. So it's 18 basically. So this line is the one that we want. We have like 215, so somewhere here, and when it's come to 18, so it gives you around like 0.7, okay? So this is your suction factor is 0.7, okay, from the graph. Now, the equivalent flow factor, now you look into the off-gas temperature. Now, in our case, off-gas temperature was 40, so it's this line here. And then you look into the molecular weight of your off-gas, which is in our case is 50, right? So it's this line here, right? So you have the 40 with the 50, this 40 coming here, intersect with the 50 at around 1.2.2, okay, 1.22, okay? Now, you could calculate your your equivalent water suction flow, which is your off-gas flow, multiplied with your equivalent flow factor, divide by your suction factor, okay? Now, we need to convert that into steam consumption. And so basically, we use this chart here. So this basically is your compression ratio. In our case, was 1.5, so somewhere here. And these lines, each line is for a certain expansion ratio. In our case, was 26.5, so somewhere here. Okay, so somewhere here around 1.5. Okay, so around 1.5. So it's going to be somewhere around like 0.7, say 0.7. Okay. Then simply your steam consumption, basically it's your equivalent water suction flow multiplied with that ratio we just found out. Okay. So that would be this multiplied with that. Then this flow you give to the vendor, and the vendor would tell you if you could just do 1 steam jet or 2 steam jet in parallel. Because that depends on the rating of the steam jet. Maybe the steam jet could only handle like 800 kilogram per hour. Then you could do 2 in parallel. Okay, and that's it. If you like the video, please share and subscribe. If you have any question, please email me. My email is on the bio. And thanks a lot for watching.